Okay, are there any questions before we start? Today I'd like to talk about current mirrors and talk about signal swing. Current mirrors for the purpose of trying to use them to improve the characteristic of an operational amplifier or change. And signal swing because when we design amplifiers, we need to manage signal swings as well. So here's where we're at. We're still talking about single stage, low gain op amps. So these are some more tools we want to use to build these structures. A review from last time. We looked at a reference op amp. And we looked at the natural design parameters of that structure. We made a statement but did not show that there were 5 natural parameters and 1 constraint. So there were 4 degrees of freedom. We made the statement that the characteristics, gain and gain bandwidth product and slew rate are really complicated expressions in terms of these natural parameters. But if we go to this practical parameter domain, we saw that the expressions for the gain bandwidth product, and the slew rate were really simple, almost decoupled. We talked about tail current and tail voltage bias. We hopefully looked at the benefits and the limitations of both. There are trade-offs between which you use. The small signal gain expressions, differential gain expressions were the same. The common mode gain expressions were different between these structures we observed. Then we defined slew rate. And that's the maximum rate of change at the output. And we made the statement that for most op amps, the positive going slew rate and the negative going slew rate are the same. So we just denote that as the slew rate. Here was the reference op amp that we looked at. And here are 3 characteristics of that op amp in terms of mixed parameters, small signal parameters, and bias currents. But on the right, all of those properties are expressed in terms of what I call the practical parameter domain. Important thing to observe in the structure is that there was only one of these parameters that affect the gain. What's that? Excess bias. The excess bias of that N-channel transistor determines the gain. And once the gain is determined, once the gain is fixed, how do we adjust the gain bandwidth? With what? Power. If you want a factor of 10 improvement in the increase in the gain bandwidth product, it costs you a factor of 10 in power dissipation. Those are ruthless trade-offs. When you want to speed something up, you use up really valuable resources. And the slew rate for this architecture, once you fix the gain bandwidth product and the gain, you have no control over the slew rate. It's fixed as well. Make sense? And then we summarized the characteristics of first the single stage amplifier structure and now the reference op amp in terms of both the practical parameters and the small signal parameters. We mentioned earlier there was a little caveat. It says need a combo feedback circuit to establish VB1 or VB2. And we said that the combo feedback circuit takes the difference, takes the average of these 2 values, and then compares it to what we would like the quiescent value to be, and generates a feedback signal to control the biasing of either the P-channel device on top or the tail transistor on the bottom. The combo feedback circuit is often quite large, and even though I have not talked about it yet, there's a modest amount of effort that goes into the design of the combo feedback circuit as well. So we can ask the question, can we remove the combo feedback circuit? If we can eliminate the combo feedback circuit, that would certainly be an attractive property. So I'd like to look at the operation of the op amp now from a slightly different perspective. What's happening on this structure, if we look at the half circuit for the differential gain calculation, what we're doing is we're steering a current that's GM1 times V1 We're steering that current into the output node, and at the output node we see three impedances. We see the impedance associated with conductance G1, the impedance associated with conductance G2. Those are the output conductances of the counterpart network and the quarter network, respectively, and we see the load capacitance CL. So we're steering a current into that load. And the analysis was real easy when we analyzed the circuit, because all we had to do was sum currents to this one node, and from that we were able to get the gain and the gain bandwidth product and the bandwidth, right? If the signal-dependent current could be doubled or increased, this current here, if we could increase this but didn't change the conductances, we would do two things. We would increase the gain, and we could increase the gain bandwidth product, because the bandwidth wouldn't change either. So let's consider now a different way to bias that counterpart circuit. Instead of biasing the counterpart circuit with a DC voltage VBB, I'm showing on both sides, but it's a single voltage. What if I bias this counterpart circuit by connecting the input to the output node on the left? If the input impedance of the counterpart circuit is infinite, connecting the bias port of the quarter circuit to Vout instead of to VBB will cause the signal current in the right counterpart circuit to be approximately equal to that in the left counterpart circuit. Now let's see what we mean by that. So when we put a differential input in, we have a signal current coming here and a signal current coming here. One is going up and one is going down. When we analyzed the circuit initially, any signal-dependent current that was on the left side of the circuit did not ever make its way over to the right part of the circuit. It made itself to the counterpart circuit over here and to this output capacitor. It did not make it to the right side of the circuit. If I tie this around here, this current here will also be the current flowing here. And if this voltages are the same for the two counterpart circuits, the signal current flowing here will be equal to the signal current flowing here. And consequently, it looks like this has potential for steering more signal current to the output node. We're already steering signal current to the output node through the counterpart circuit, through the quarter circuit. But in this case, we're going to mirror some current to the signal current to the load through the counterpart circuit. This kind of a connection, if the output impedance is high, forms what's called a current mirror. And if the signal current that we steer to the output is the same as the signal current in that quarter circuit on the left, we will double the amount of signal current that's being steered to the load. Furthermore, you could show that if you bias the circuit this way, we no longer have to have a separate DC bias voltage to establish the operating point for the counterpart circuits. So we eliminate the need for a common feedback circuit. Now this circuit is no longer symmetric. On the left side, we have a connection of the biasing point of the counter circuits to the output node. On the right, we don't. So if the current IB is small compared to IN, and the current IN is nearly independent of the voltage across it, then I out, this current here, is approximately equal to IN. Of course, we could make those gains actually, if we change the sizing of the devices, we could even make a gain from I out to IN, or an attenuation. So these kind of circuits are called current mirrors. So now I'd like to consider using a single NMOS transistor as a quarter circuit. We'll see what happens then if we use this for the counterpart circuit and connect the gate around to the drain. So instead of connecting this to bias voltage, we connect this around here. And we recognize this as the basic current mirror we looked at in 330. We see this P-channel current mirror on top here. This current here is the same as this current here. So in this case, the counterpart circuit, as we conjectured, becomes a current mirror. Current mirrors are just really current amplifiers. The current mirror eliminates the combo feedback circuit in this architecture and many other architectures. In this case, the gain doubles. Because if you go back to this circuit right here, the current that's steered to this node is steered to the output. So we have the sum of two currents coming into this node now. The current coming through M2 and the current coming through M4. They're both equal in magnitude and opposite in phase, so that doubles the current we steer to the load. But the output impedance hasn't changed. Although I looked at a simple current mirror derived from the counterpart circuit, I could put other current mirrors in there as well. The current mirror does not necessarily have to be derived from the counterpart circuit. It could be derived from counterpart circuits for other quarter circuits or any other current mirrors that we've worked with. If we look at the basic current mirror, we did this derivation in 330. The input current is given by saturation region equation. The output current is, we take the ratio, everything cancels, since the gate to source voltage are the same, except the W over L ratios. So this was the gain of the current mirror. And that gain is true irrespective of whether you're looking at large signal inputs or small signal inputs. Small signal model of the current mirror, put in the small signal model of the transistors, and we get this. But GM1 is typically much bigger than GOut1, so you can approximate that by doing GM1 here. And GOut1 is typically small compared to GM1, so it's typically the ratio of the two GMs times I1. Of course, those ratio of the two GMs is the same as the ratio of the W over Ls. So here's a small signal equivalent circuit for this current mirror. Question?
Yeah, I do have one. So you said we've lost symmetry now, right?
Yeah.
I guess I don't see that because right that current mirror is going to the gates of those PMOS transistors, right? So we're not losing any current going into those gates, right?
It's okay. First of all, the reason we've lost symmetry is if you look at the circuit to the left and to the right, we don't see the same thing.
Sure.
Okay, so that was why I said we lost symmetry. But now, what was your other question?
You assumed non-zero current going into those gates of those counterparts now, right? Current.
Yes.
Okay.
If you don't have non-zero current, then you don't have a perfect current mirror. If you have a bipolar device, you have a little base current flowing, for example. But if there's no current that flows here, then this current and this current, if we set it for a mirror gain of 1, this current and this current will be the same. They'll be the same DC-wise, they'll be the same small signal-wise. Did I answer your question?
Yeah, you did.
Yes?
Can I understand how we double the current?
Yes.
On the right side.
So the current here is going to be GM1 times VD over 2. That's the current we're going to get here if we have a differential excitation. The current here will be the same current but opposite sign. So this will be minus GM1 times VD over 2. And that's the same as this current here. So this current is going to be GM1 over 2 times VD. This current here is going to be minus GM1 VD over 2. So if you look at the current that's run to the load, CL, I don't show the load here, the current will be the sum of those two currents. Okay.
Is that because the tail biasing is only going to pull a certain amount through that?
Tail biasing is fixed.
Yeah, so
Right.
even though you increase the current that's going to the right side, what's going to come out of the tail is going to be consistent.
I don't increase the current here at all.
Yeah.
So if you look at the right side, I'm going to have a current here that's going to be GM1 over 2 times VD. If I have a differential excitation. The 2 comes from the differential excitation. I'm going to have a current here. So this current here is this current over here was this current coming down was minus GM1 over 2 VD, right? Because we have a symmetric excitation, symmetric differential excitation on the device. So this current here is going to be minus GM1 over 2 VD. So this current here is going to be this minus this. So it's going to be minus GM1 over 2 VD minus GM1 over 2 VD, which is equal to minus GM1 VD. So the current we're steering to the load here is now twice as big as it was before. Does that answer your question?
Yes.
Okay. I should have shown the load capacitance on there to indicate that we were steering that current to the load. Well, we're steering it 2 places. If you look at this output node, if put in a small signal equivalent, there are 3 things hanging on this node. We're steering it to the capacitor and the 2 output conductances. Those 2 output conductances don't change. So remember, there's an output conductance, capital G2 here. And there's a conductance, capital G1 here. So the current that's delivered, that's steered there, the current that's steered there is doubled, but the total conductance is capital G1 plus capital G2 plus SCL. Yes?
So could we increase our gain even more if we were able to increase the output impedance of our current?
Absolutely, absolutely. Great idea. So don't forget that idea. We're going to come back and look at things to do that with. Right now we're leaving, by creating this as a current mirror, we haven't touched the output conductance. The output conductance of this circuit is the same as it is if we put a DC voltage bias here. The reason the conductance is the same is we haven't changed the quiescent current. Tail current stays the same. If the tail current stays the same, the output conductance here stays the same, and the output conductance here stays the same. Good observation. I like the thought process. We asked the question, what can we do to increase the gain? One thing we can do is to make the conductance smaller. The other thing we can do is steer more current to that node. Or both. P-channel current mirrors the same thing. So, more advanced current mirrors exist. Your author talks about quite a few current mirrors in the textbook. We can also have gain on our current mirrors. And if we have gain on the current mirrors, we can steer more current to the load as well. We'll go back and look at that as well. The several properties of current mirrors that we're concerned about, not only for op amps, but when we get into data converters, we will not be so concerned about mirror gain accuracy for op amps, but we will use current mirrors a lot in data converters, and there the mirror gain accuracy will be really important. We will be interested in the signal swing at the output of the current mirror. because the current mirror also sits on the output node. If the current mirror doesn't have much signal swing, we won't have much signal swing on the output of our op amp. Also, the output impedance of the current mirrors are important. As Mr. Kimmler pointed out, if we could drive the output impedance of that current mirror up, we would probably drive the gain of our amplifier up. If you look at the more advanced current mirrors, they usually offer improvements in one or more of these properties. Here are three of the more popular current mirrors. The one on the left is called the Cascode current mirror, the one in the middle, the Wilson current mirror, and the one on the right, the modified Wilson current mirror. And they all have the same basic current mirror gain. We can see the current mirror gain by looking at the lower part of these three mirrors. M1 and M2 determine the relationship between this current and this current. And that relationship is the same here, and it's the same here. It makes no difference whether we have the diode connected transistor on the left or the right. If the mirror gain is 1, they'll have the same relationship between the currents. These extra transistors that are added primarily to increase the output impedance of the current mirrors. Okay. But unfortunately, since we're stacking more transistors in series, it's typically at the expense of a reduction in the signal swing at the output of the current mirrors. I recall when I was first teaching a course like this, there were 3 of us working on the course, and I knew the least about the material. And somehow we decided on what an outline was going to be, and we decided one lecture was going to be on current mirrors. Randy Geiger drew the straw with current mirrors on it. And Randy Geiger didn't know what a current mirror was. So I tried to go, this was in about 1981. So I tried to go to the literature to find out what a current mirror was. Had a hard time finding somebody defining what a current mirror was. I finally figured out what one was at about 4 o'clock in the morning, and I think my lecture was at 9 or something. Hopefully those students that took the class learned something about current mirrors. Anyway, the concept of a current mirror was introduced, I think, in 1969. After I couldn't find what a current mirror was, couldn't find it in a textbook, and in the literature I saw current mirrors being used after I figured out what one was, but the earlier papers on op amps did call them current mirrors. And they didn't draw them like we draw them now. So we almost always will draw a current mirror like this. You know, so this would be a P-channel current mirror, right? And if so I'll give another example. If you look at a bridge circuit, we almost always draw a bridge circuit like this. Right? We draw bridge circuits like this.
Yes.
We draw current mirrors like this. Why do we draw a bridge circuit like this?
It's easier.
I don't know. I think it's more confusing.
What?
Convention?
Convention. 45-degree lines out. We don't do it for anything else, but we do it for a bridge circuit. Current mirror. Why do we draw it like this? Well, you go back to the first op amp started to appear in about 68, 67, maybe 66. And they didn't draw the current mirrors like this. And they didn't even, when they analyzed the circuits, they didn't even make the observation that the currents were ratioed by the W/L ratios. So the first paper I saw that used the term current mirror was a paper titled OT Obsoletes the Op Amp by Wheatley and Whitlinger. And so I finally called those guys up. They were working for RCA. And I asked Whitlinger, he didn't know too much about it. I asked Wheatley. And Wheatley said, he said, we had a patent that we were filing. And he said, I think that between me and my patent attorney, we decided to call that part of the circuit a current mirror. So I think that's where a current mirror comes from. I think that Wheatley and his patent attorney used the term current mirror in a patent and then subsequently in a paper they published about the corresponding circuit. How many current mirror circuits are there? We've looked at 4, the basic current mirror and these 3 others, right? We've probably got current mirrors pretty well. Oh, by the way, these circuits we looked at, these other 3, they appeared shortly after the original current mirrors appeared. They date back to the early 70s. Have we seen any current mirrors come out lately? Is there still an opportunity to contribute in the current mirror field?
I think so.
Yeah. So last night, I got distracted, and I decided I'd find out. First of all, I didn't know if I could do this or not. U.S. Patent Office is not shut down. There was a big note on their website. It says we are still functional. We collect our revenue from people that file patents, and we've got enough revenue to operate. And so I did a search for patents in the U.S. Patent Office website with the words current and mirror in the title. And this goes back to 1976. This doesn't quite go back far enough because some of those first current mirrors were prior to 1976. And unfortunately, we only have images. We don't have full text search capabilities in the U.S. Patent Office. But there have been 569 patents with current mirror in the title since 1976. This happens to be January of 2018. So these are sequential in order. And you can see some of these are current mirrors and some are using current mirrors in other circuits. So there's 569 since 1976. I did this 4 years ago, and there were 509 at that time using the same search. So, and I did it 2 years before that, and there was 475. So what can we conclude? There were 26 patents with current mirror in the title in 2016 and 2017. They averaged 12.4 patents per year from 76 to 2006, averaged 17 per year in 2012 and 2013. There was a little bit of a blip there. 13 per year last year and the year before. The number of patents per year right now is about the same as it's been on the 3-decade average. So, I asked the question, Mr. Kimmler says, yeah, there's probably an opportunity to contribute. We still see patents coming out on people introducing current mirrors. How many current mirrors are there?
69.
This doesn't include the ones up till 1976. Now, they're not all current mirrors. Some of them are using a current mirror to build something else, but quite a few of them are current mirrors. If you come up with a current mirror and you're working for a company, do you think they're going to patent it, a new current mirror?
Yes, for sure.
Company secret.
Yeah, you might want to keep it on the down low.
So, I'll make a comment about that. It would be easy to patent. There are new patent ideas that come up very easily now on new current mirrors. In fact, if I challenged everybody in the class to come up with a new current mirror, my guess is within a relatively short amount of time, everybody could come up with a new current mirror that has some properties that were different than properties that other people had that might be interesting. I'm confident we could do that. As far as getting a patent is concerned, if you put a current mirror in a circuit and your competitor uses it, you've got to know that the competitor's using it to be able to collect royalties or collect licensing fees. If you work for a company, you may not be encouraged to tell your competitors what you're putting on the inside. Circuits are sufficiently complex that it's a major effort for somebody to go in right now and look and see if you're using their IP on something like a current mirror. So oftentimes, circuits like this, companies will choose not to file for a patent, not necessarily because they want to protect it as IP, but because the value of the patent is maybe questionable. If they don't know the customer's using it, they can't collect royalties from that. In spite of that, we still see quite a few being patented. So my guess is the number of current mirrors that have come out is much larger than what we see in the patent literature, because there's a reluctance to oftentimes patent clever circuit ideas if you don't have the ability to generate revenue from royalties on those patents. Makes sense? Oh, if we were to go look at those patents, it's kind of fun to do it as an academic. But I visit with quite a few engineers in industry that are oftentimes instructed not to look at the patent literature. Don't look at the patent literature. Don't go to do a Google search or US Patent Office search on current mirrors, even if you need a new current mirror. Why do you think they instruct engineers not to look at the patent literature?
So they have plausible deniability if they use somebody's patent.
Yeah. If they knowingly use somebody's patent and it litigates, they have more liability than if they did it without knowing about it. So I don't think they usually get words that says, don't look at what's in the textbooks. I can give you examples of some of these patents that are also published in journal papers and in textbooks. And if you use them, you're still compromising or you're still infringing on a patent if it was published in a textbook or a journal article. You're not expected to, nor obligated to, nor do people usually put notation in a textbook or journal article if they file for a patent. So I don't think that people from industry are discouraged from using textbooks or journal papers, even though the material in those might be patented. Is that ethical? Asking people you're expected to be knowledgeable about the world around you. We've got this great resource of information from the US Patent Office. And now we have good search engines that allow us to find stuff in that database pretty easily. You think it's ethical to ask people to not learn about that information that's available that might help them do their job better? Should be allowed to look for it, shouldn't it? It's unfortunate. I tend to agree. I think it's somewhat unethical to ask people not to be aware of what's around them strictly for legal reasons, but that's probably reality right now in most companies today. Okay, so here's another single stage low gain amplifier. This amplifier has double the gain of the one on the left, but we lose the second output. So what are the pros and cons? We get a doubling of gain, we get a doubling of gain bandwidth product, but we give up the differential output. If you're building a catalog part, is giving up the differential output a big deal? No. Almost no catalog parts have a differential output. I don't understand why. If you're building an op-amp for an integrated application, giving up this output is often a big deal. Because almost all linear circuits that are built on silicon will be fully differential. That means you probably got to go put the combo feedback circuit in to generate the bias points. How about the slew rate? When VD is large and negative, VD is equal to Vn plus minus Vn minus, this voltage here is large. This voltage is small, the tail current will all be steered to this side. Since there's a current mirror here, if the current is all steered to this side, this current will be what? It'll be zero. So the current that's going to be flowing here is going to be the tail current. So remember, the slew rate was the current that goes to capacitor divided by the capacitance, so the current will be I tail over CL. When we had a DC bias voltage on that instead of a current mirror, what current did we steer to the load? We steered IT over 2 to the load. Because we still had a current here flowing of I tail over 2 out of the upper devices. Put I tail here, so the net current that went to the load was I tail over 2. So what does this do to us to the slew rate? Increases a factor of 2. So we double the slew rate with this current mirror on top. So that's another advantage of the circuit. Disadvantages, we lose a differential output. Advantages, we eliminate the combo feedback circuit, and we double the slew rate. And of course, double the gain and double the gain bandwidth product. So here's the corresponding expressions for this structure here. Have we done much analysis yet? Or have we been writing stuff down by inspection? Writing it down by inspection. Signal swing. I'm going to first look at signal swing on the single input, single output structure. To keep M1 out of triode region, VDS has to be bigger than VGS minus VT. VDS is V out here. So V out, and VGS minus VT, VGS is Vn. So VDS, V out has to be bigger than Vn minus VTn. To keep M1 out of cutoff, we want to keep this in saturation, right? So to keep it out of cutoff, the gauge to source voltage has to be bigger than the threshold voltage. VGS is Vn has to be bigger than the threshold voltage. To keep M2, if we let this voltage get too high, this device will go into triode region, and our gain will drop down. So to keep M2 out of triode region, VDS, which is the magnitude of V out minus VDD, it's actually V minus V out. It has to be bigger than VGS minus VT, which is the magnitude of VXX minus VDD minus VTP. And you can rewrite this in this form. So if I look at this in the V out Vn plane, these three conditions define what? Lines. This is line 1, this is line 2, and this is line 3. So it's these three lines that define the input and output signal swing of this device. Yes?
What were the axes? What plane are you mentioning?
V in and V out.
Yeah.
We define signal swing relative to what the input can do and what the output can do. So we want to get the signal swing in the V out, V in plane. So, line 1, it has a slope 1, and it says V out is bigger, that means it's above this line. Line 2 says Vn bigger than Vtn, this is Vn equal Vtn, bigger means it's to the right of this line. And the line 3, it says V out has to be less than Vxx minus Vtp, that's this line here, it has to be below. So that means the operation region of this device is defined by this triangle here. Okay. Do we have good signal swing on this structure? Do we have good output swing?
We have good outputs.
Well, it depends. If the combo input is small, we have good output swing. If the common input is large, we have a small output swing. Does it make sense?
Yeah.
So we can control how much swing we have by controlling where we bias it at.
So that's why we use a chip current to bias because it's
This has a good common input range with a tail current bias. But on this circuit here, I don't have a tail current bias. I'm looking at a different amplifier right now. Okay? We can come back and do this with the other structures as well. So I'm most interested in the process of how we find signal swing, and I've looked at this structure initially. So if I look at the transfer characteristics of this device, the transfer characteristics look something like this red curve. For Vn small, this transistor is cut off and the output is VCC, and eventually it comes down like this. And this is the high gain region. This is where we want to use it as an amplifier. And the gain in this region, we calculated the gain earlier in the small signal domain. But what did we really calculate? We calculated the slope of these transfer characteristics. So we can either look at the DC transfer characteristics and calculate the slope, or go to the small signal parameter domain and calculate in terms of small signal parameters. So the same. How do the transfer characteristics now relate to the gain? Because when we design this amplifier, we might want to design it to have high gain or low gain. Are the gains that we choose going to affect the signal swing we get? There's only degrees of freedom available in a design like this. So here's a plot of the transfer characteristics of this structure as a function of the gain. And we see that for increasing the gain, slope gets steeper, we get more signal swing on the output. For less gain, we have less signal swing on the output. How about this op amp? This one with the current mirror load. I do this for any op amp structure. Well, there's a region of operation where the device will all be in saturation, where we're in the high gain mode. So this is the V out, V in common plane, and I've got some boundary where the device will be operating. Generally, large signal swings come at the expense of other desirable characteristics. So generally, if you try to design your circuit to have a large signal swing, something else will probably not be so good. If we have small signal swings, a lot of other characteristics may be better. So let's ask the question, what type of signal swing is needed? We know how to calculate it. Be careful what you ask for, because you may ask for things you don't need, and you may pay the price in performance for doing that. So in the upper left, I'm showing a situation where we have wide common mode input range and wide output range. This structure here has a very narrow input range, but a wide output range. This structure here has a wide input range, a very narrow output range. And this structure here doesn't have much range on either the input or the output. Can we conclude that the one on the upper left is much better than the one on the lower right? Depends on the application. Would we ever need something like this that doesn't have much signal swing on the input and doesn't have much signal swing on the output?
What are you trading?
Yeah, well, it depends on the application. So let me look at this circuit right here. I look at this circuit here. What's my comm mode input to the amplifier? What? Zero. Does that change?
No.
No, it's going to be a few microvolts maybe, right? Do I need a large comm mode input range on the op amp if I'm going to use it in this application? No. So this would be completely acceptable for an op amp used in that application. Make sense? How about this circuit? What's the comm mode input range now? What?
Still zero.
Common mode input. Common mode input is VN. If VN was a big signal, this circuit requires a large common mode input range. Would an op amp that had this characteristic be suitable for this application? No. We need something like this. Or in this case, we might need something like this. There's a lot of difference between designing a catalog part and designing a part that's used for a particular application. For a catalog part, we would like one solution that will fit in a whole bunch of sockets. We'd like to put it in a socket that does this, a socket that does what we had before, and a whole bunch of other things. So we'd like large common input range, large output range. But in an integrated application, you know what the application is going to be. So you don't necessarily want to pay the penalty of degrading other parameters for characteristics that you won't use. So upper left expected for catalog parts. Upper right acceptable when the comm mode voltage is fixed or very narrow. This is acceptable when followed by a high gain stage. If you have a two-stage structure and the gain of the second stage is large, the first stage can't swing much. So you don't need much signal swing. And the one on the lower right is good when there's a narrow common mode input range as dictated by an application, and it might be a first stage in an amplifier. Make sense? So all of these situations have entirely different performance characteristics, and all are useful. Oh, that's the last slide. Are there any questions? That's all for today. Thanks.